Okay, so I think we could start with the triple integrals, okay, and focus on how to change the order, okay, in triple integrals. So suppose that we have this question here. So express the iterated integral. We have the questions there. So triple integral from 0 to 1, 0x squared, 0 to y, then it will be dz, dy, dx. And we are going to change the order. So from dz, dy, dx, the first is we change to dx, dz, dy, and then dy, dx, dz. So what's the thing that you need to do first is basically, if you can draw the triple integrals, I think we can draw. And how to set the graph. So we set the x, y, z axis. We set, first is look at the first layer, or the outside layer, which is 0 to 1, which is the dx. So we say that from 0 to 1 for x, okay? And then we see the dy. So we see the area on the xy plane, okay? So y is, so let me write here to make it easy. So we know that x is from 0 to 1, okay? And y is from 0 to x squared, okay? And these two, they are our dA, okay? They are our dA in the xy plane. So I think these two can be easily sketched. This, right? This is the x squared. And then we can imagine from 0 to 1. So this will be our first step to draw, okay? And then we have z. Z in our endpoints is getting from 0 to y. So if we could imagine, if we see only on z and y plane, so which means this is z, this is y. Z equal y will be this line, right? On this zy plane. But remember, z is function of two variables. So we need to set up z and y, and we need to also include x, which is, x is related to y is x squared. So this we could say that z is less equal x squared. Okay? But then we have x squared is here. So we need to make the line z equal 1, which is here. We need to move out and then take for x equals 0 to 1. And then we can also see that when z is less equal y and y is less equal x squared, if we check with some numbers 0 to 1, this will precisely get in this line. Okay? And then what we can do after this is basically we can project it, all these endpoints into three different projections. D1, D2, D3. Okay? So this will be D1, which is XY plane. And then ZY plane, which is here. So if we see from this side, okay? And then XZ plane. XZ plane we see from here. Okay? We see from this side. So we see that this is going to be exactly this. Okay? And it is the same from 0 to 1. So after we get this three projection, what we can do for the, so if we want to, first is our goal is to make it into dx, dz, dy. So first thing, we could see the dy. So we need to make a constant on dy. So y, we could see that y is, we could state y, if you look at the 3 dimensions, it's all the same, 0 to 1. So let's just use that one. So 0 to 1 for y. Okay. So let's just write y. So let's say E is our solids. So we have x, y, z. So 0 to 1. And then the second one will be z. So we can treat this yz. Yz is here. This is our, let's say in double integral is similar to what we have as dA. So let's say this is our dA. So 0, 1, okay, for y, and then z will be start from. Okay, now this is different. If we say z is from 0 to 0 to 1, or z equal y to 1, then we have different triangles. This is the triangle here, right? But if the triangle is this one, we say z start from 0, and the top point is this line, right? So 0 to the z equal y. Okay, do you get it? If we say it start from, let's say, z equal y, we start from z equal y to z equal 1, which is here, then this will be the triangle, right? Wrong triangle. But here, we start from the z equal 0, and then it's supposed to be go up, right? For z, it's supposed to be go up, but the upper point is limited by this line, okay? So that's why we have z start from 0 to 1. And then, how about the x? Now x, we need to treat x as a function of yz, which means that we are going to see x within this case. Okay? So if we see, so within this part here, that x is actually square root of z. And z is equal y, so x is also square root of y. Okay? So we could write that x, okay, so x will be this axis, okay? So we want to go to let them from this surface to this surface. So what will be the better way to state that part is we can write square root of y less equal x less equal 1. So how do we get this 1 and square root of y? It's actually, it starts from here. So if you see, this is our x, okay? And then if we project it through this way here, you see that this will be 1, okay? This will be this curve here, which is related to the projection of this. Or we say this is the square of y or square of z. We can say square of z, okay, first. But since this is related to two variables, we need to state with the different variables. So this will be square of y, and then this will be 1. Okay. So then the triple integral we can write. This is 0, 1, 0, y. This is square root of y, 1. And fxyz dx dz
Wait. dy, right? So the key is to state the first two. Okay? I think the first two is based on this, either this tree, okay? One of these three. And this last one will be the surface, actually the surface. I think to make sure that, I think for the first two one is okay, right? The plane, okay, whatever that's real. I think this one, we need to have like a good imagination. So let me draw what that means. Okay, what that means. Let me draw. So x equal 1 is here. So let me write here. This is, so we have some big plane like that, okay? X equal 1, okay? And then we have the square root of y or square root of z. This is actually this one here. So this is actually the projection here. So it's like a surface. So this surface, whole thing, minus this. Or this is the upper point, and this will be the lower point. We see from this will be the top, and this will be the bottom. Okay? Difficult, right? Yeah, but this is a difficult question. Well, let's see the second one. Okay, the second one maybe better. The second question is asking dy, dx, dz. Okay, dy, dx, dz. So we first state the last one, which is will be the constant. So this will be in xz plane. So let me write here. So this will be yz plane. This will be xz plane. In xz plane, let me erase this part first. In xz plane, we have the z is 0 to 1. So we need to state the constant, right? The constant first, this is the constant. And x should be a function of z, right? So we need to write x is equal square root of z. We need to write in terms of x equals square root of z. So if this is start from 0 to 1, okay. Now what would be better to state the x, which is going from left to right? So it's better to start with the curve and ends up with x equal 1. Okay? I hope that's clear. So we state that the solid E start from 0 to 1, and then the Z will be start from square root of Z less x less than 1. Okay, and then what will be the last one? The last one will be the surface of function of two variables. Now we are going to have dy. Now dy, we need to write, since dy is going to be that axis, right? So we need to see which one is the surface. So the surface is, we have this line. So we have this line here, and we have this line. Okay, but we need to write that in terms of y. Okay, so y is the function itself. So we need to write as a function of z and x, or both, at least two variables. Okay. But it can be one variable, but we need to include both. Okay. So this will be, we can state that this will be start from this line z equal y, or we say y equals z, and then ends up with y equal, what will be this one? This one is related to this yx squared, right? This is yx squared, and since y equals z, then we say also this could be y equal, or this will be z, okay. Z equal x squared also, we can state that. So this will be stating the x squared. Okay. So this will be the z less equal y less equal x squared. So this will be 0, 1. dy dx dz. So again, this part here, maybe if we draw like we have a surface here, and we have a surface there, which is the x squared. So this is the surface, and this is the another surface. I think maybe if I draw like this, maybe it can help. So this will be maybe that. So this is the plane. Y equals z. Okay. So that, and then it goes down here, which is this part here. Yeah, very difficult to draw, but yeah, but suppose that will be the plane. But anyway, okay. Or maybe this is easier like this. If this is having the plane, okay, that is y(x squared), okay, and the other plane is y equals z, which is going to be this plane here. So there are some intersection in between, and we stay from this y equals z to this y equals square like that. I hope I can, but I think that my drawing is not clear. But it's actually, we start like y equals z, this plane, and then we move to this boundary here. So this is the left and right boundary, or bottom and top boundary. Well, anyway, maybe I can give you more explanation. I think I will find the better way to explain this, but yeah. Yeah, this was the y equals z, right? This one, and this one the x squared. So this minus this, this is the up, this is the up. I think we can try using the GeoGebra, but I think later we can try. Okay. I don't think I have time for today, maybe tomorrow. Okay, so this is just an intro for the changing for the order of in triple integrals. Okay, so let me write here. Please check using graph in any website that you can find. Maybe GeoGebra is the best way. Try 3D 3D axis in 3D axis. Okay. So basically, the way we do this is first is finding the first two plane, or the dA, the area first, and then find the surface. I think the area is based on the projections. Okay, so find this first. So which means it's the first two, all the first two, and then, or the last one, sorry, the last one, and then this last two, and then the surface will be this one, and the inside integrations. Okay, now I will move a little bit to, it's actually in chapter 15, the last part, which we have now. We call it changes of variables. Or we call this is, typically we say the Jacobian. Okay? So we skip the triple integrals for sphere, for cylinder. So we skip all the way. So suppose that we have this, okay? We have this condition that T is representing transformation. and transformation can be anything. But in here, we imagine that there are different planes. So we have a UV plane and XY plane. So if the T represents transformation from UV plane to XY, and then we have the inverse also, the T inverse that is going from XY to UV, okay? So if there is no points that have, or no 2 points have the same image, we call this is one-to-one function, like the inverse definition that we have as usual. So if we state the transformation like in terms of another function g, xy, and then v, let's say h, xy. So we can try to solve this and then find how they are connected. Okay. Now to make it easy, we can try for some example in a function. So let's say we have a transformation that is defined by this x and y. So we have u squared minus v squared and then 2uv for y. And then we need to find the image of the new in the new plane, which is we define as S. So we state from S, from U 0 to 1 and V 0 to 1. Okay. So we start to map based on this S. Okay. So this is our S, which is state from 0 to 1 for U and 0 to 1 for V. Okay. And then we see that we have 4 different paths, right? So first one is S1, we start from 0 to 1 for U, and the V is 0, and then here stay from 0 to 1 for V, and this U is 0, and the same thing with this, and we have this four paths. And then we need to map all this into xy. So we could say that we could let first, maybe we define by one by one. So S1 is mapped from 0, 0 to 1, 0, right? I think there is no big deal, because when we take this and then through the relations U and V, practically we just move out the x-axis, right? Here. Move out there. So this is for V. So let V equal 0. And then U is from 0 to 1. And then for S2, so this means that, let me write here, x equals 0 to x equal 1, or here is yeah, 1, right. And then we map S2, which is this going to be, let U is 1, and then start from the phi is getting from 0 to 1. Okay. So if we put this, so we have the x is 1 minus we can exchange phi become y over 2u, okay, and u is 1, so this will be y over 2 and then squared, so we have y squared over 4, and then we see that we can try see from x equals 0 to x equals 1, which is, this will be a parabola, right, which is a parabola. And then the S3, we see that when phi is 1 and then we move the u, and then the same way we are going to get that x is, so u squared minus phi squared, so phi now is 1, so u squared will be, we can get from here as well, y over 2v, so the same parabola but in terms of the left one, so this will be y squared over 4 minus 1, so it will be identical parabola, okay, so for the S3. And then the S4 is given when u is 0, and then we can state that 0 to 1 for v, and that is when x is actually 0 minus phi squared or minus phi squared. So we know that since y is 0, and this will be state from -1 to 0. So this is how it looks like. So we state from the first one, so this is the first one, S1, and then S2, and then S3, another parabola, and then the S4. Okay, so this is all based on the transformation that is being given. Okay? Now our goal is not only for how to create a new image based on this transformation, but we need to see, is there some sort of multipliers that is enable this transformation to happen, and then when we are using that the multiplier for that transformation, we can simply changing all the integrations variables into another variables based on the transformation. And the idea itself is not to make things complicated, but sometimes when we have an integration and maybe it's too difficult to see, we can just change the equation itself by the transformation to make the integrations quite simple. And these transformations also can be imagined as a transformation in machine process, like in machine learning and logarithm, some algorithm inside that can be transformed using matrix. Usually that is how the machine works in computer. So your computer then have some sort of transformation inside, and this is one way to see how the transformation looks like if we try to look on the image. Okay, so we can try and alter the image. So to begin the transformations, then we can say let's look on these two images here. So let's say we have S and R, and we also state that we have our transformation T. So imagine that we are going to transform the left to the right, okay? And we are defining all the information. So this image so let me write image of S is a region R in XY plane. In which the boundary point x0, y0 is basically based on transformation T of u0, phi0. And then we state the vectors for the R. So this R is a vector in U of U phi is G of U phi and we state these two functions that is going to be component of I and J or XY. So it's the vector position. And then imagine that this vector has a tangent vector. So the tangent vector means that this will be this and that. Okay, that's the tangent vector. So tangent vector first is the tangent vector for U. Let me write. So we are going to tangent vector with respect to U. So this will be G of U. This will be U0 phi 0 I plus H U U0 phi 0 J. Or in this case, we can state that this will be partial with respect to U. Okay. This is partial for Y with respect to U. And the same way we are going to take the partial with respect to V. So this will be G V and H V. And this will be partial with respect to phi. Now if we imagine that the vectors here, we have A and B, and we know that the definition for these two vectors is basically, if we see the B, the change only on V. So we need to plus delta V on the V0. And this one, the A, is changing in U. So U0 plus delta. This is similar to what we have in partial derivative when we explain the tangent plane, tangent vector. Okay. So we have A and B. So we can represent A and B in terms of vector positions. That is, the A, the vector A is differences between these two vectors, and B also the same. Okay, but then the relations for A to our partial, so if we relate this to the RU and RV, the RU, based on our definition in partial, this is limit when delta U is getting close to 0. This is R. This is delta U, phi 0 minus R, U0 phi 0, and this is delta U. Okay. And then we get that approximately, to solving this becomes R. So we just cross multiply. U0 plus delta U, phi 0 minus R. R is the vector position. And then this will be approximate with the R or delta U multiply with R U. And similarly for RV, I will not write the whole thing. So I will just write for RV will be U0 and then V0 plus delta V minus same. This is approximately delta V RV. So we could have this expression here, okay, which then this is creating another plane, the green one here. And we can find the area of these two vectors with the cross product for parallelogram. If you remember that we can also find the area. So area between the delta VRU and delta URU or RV, sorry, is equal to this expression cross, or we could simply cross the factors only, which is only R, because the delta is scalar, so we can factor out. And delta U, delta V. Okay, I will continue tomorrow this part, okay? And after we cross the product, we will get the relations and the simplified form for the transformation, okay?